Okay, let's now get on to lecture part 3 of the lecture. And this has to do with time and motion of the book by Professor Cole. Trajectory is part of the motion of a robot. As you saw in an earlier lecture, perhaps on day 1, on week 1, you saw that you have robot has to work from one point to another point, has to move from a point A to point B. And you recall that the robot, let's say, has 6 motors on the 6 joints. So you have 6 control systems. Each of them is their own reference, and they all have to be generated by a trajectory for that particular joint. So you have a set of trajectory generation for joint space, and then when the robot ends up into the real world and the Cartesian space, it's the Cartesian trajectory. All of that has to be done normally by some kind of piece of code. And in this case, you may recall that one of many different polynomials you can do between point A and B, you do a 5th order polynomial, like this, which is called quintic polynomial. You have A, B, C, D, E, and F. You have 6 unknowns that you have to find, and you go from point A to maybe a waypoint, and from there you go to another waypoint, and so forth. Or you can go directly from A to B, depending on the application and the distance. So if you take the derivative of this, you get this equation. So variable f drops out because it's constant. Take one more derivative, variable e drops out, and you get now only 4 variables. So these are the values which are given to you. You have 2 values for the position, initial and final position, initial and final velocity, initial and final acceleration. These are all given to you. And here they are. When you take the derivative of this and plug the value of t equal to 0, you get 3 equations. You put the value of t equal to capital T, the final time, 3 equations, you get 6 equations. And you have 6 unknowns. There we go. A, B, C, D, E, F. So if I stack up those equations into a matrix form, I get this. Remember Kramer's rule in mathematics is very similar to that. So in order to find A, B, C, D, E, F, I multiply multiply both sides by the inverse of this matrix. Okay? So these coefficients are equal to this matrix inverse times this known vector. This known vector from what we have. And on the toolbox, the command is t-poly. Okay? Generates quintic polynomial trajectory as described by that equation. So let's say you want to use it between 0 and 1 for 50 minutes or 50 seconds or what have you. And you go through this kind of configuration. It creates that trajectory between 0 and 50 steps of 1, and it gives you the position, velocity, and acceleration vector. So, for example, here is t-poly 0, 1, 50, 0.5, and 0. This is goes to 50 intervals. Position looks like this. Velocity looks like that, and acceleration looks like that. Okay. So this is typical of what you can do. This one is the same, except initial velocity has changed. Once it was initial velocity was 0 velocity bound. V is initial velocity of 0.5 and final velocity of 0. Obviously, final velocity is always 0. Otherwise, you're going to break something. You're going to run into your material, your product. So here are some more trajectories which you can go through that. For example, hybrid trajectory, which has a constant velocity segment, like this, or here, constant segment. You go like this, and then robot goes with a constant velocity and goes back to the end effector by at the time of 50 seconds. And you may have multi-dimensional case where you have several different initial conditions and final conditions, or and you want to all produce trajectory in one shot. You could do that. Or you could have, as we did before, multi-segment trajectory. Okay, you could go from one point to another point to another point to another point. Or here we have one segment here, second, third, fourth, fifth, sixth, seventh segment. Okay. And in fact, I have produced those already in here. This is the chapter 3 of Cork. This is the trajectory of trajectory for quintic. It is the velocity, it's the acceleration. Another case in that chapter, all the way to the constant velocity segment, a stepwise trajectory, and this one is another one that you have one waypoint here, one waypoint there, and so forth. One waypoint here, one waypoint here, and so forth. And it's another one you just saw. Okay. So when you become familiar with the toolbox, and even if you're already, hopefully, if you have the time, you can take a look at what you have even before Berat's lecture. Go through the chapter, read the concept, and repeat what the author has done on the toolbox. And then the answer is already in the book, you can check it. Just basically give yourself a tutorial as you read the chapter. Okay, again, this is similar to the one that you have several waypoints. Okay. Let me see if there is anything else. Need to This is chapter 3 of Cork. Now I want to actually show you something that Berat created. Just machine vision toolbox for MATLAB. You need to, I remember we had an issue with the machine vision part last year. I presume it's okay now.
The problem was the Vision toolbox wasn't compatible with the latest robotic toolbox. So when we add the robotic toolbox into our MATLAB path, we were basically changing to or downgrading to the toolbox 9.8 instead of 9.9. So most probably this year they fixed that, and actually there is also Dr. Cork just released a open course lectures. You can have more materials in his website, and you will see it in the following slides.
So you will also go over that when you give the
Yes,
talk.
Professor.
So as you can see, the textbook covered each topic and provide examples in parallel with implementation in the toolbox. But as I said in the previous lecture, what it doesn't give you, what's the complicated equation behind it. Okay. And you can use these then while you are reviewing your lecture notes and the textbook. Robotic vision and control. So it's recommended for students to get familiarized with the textbook's content and to follow straightforward examples, which are all in the chapters. Both toolboxes are ready if you go to this website, www.petercork.com/toolboxes.html. So download it if you're not already on your laptop.
You have to download the zip folder. After you download, you basically extract it to your MATLAB directory.
That's right. And then you can also visit the discussion board, Google group page for any questions or debugging solutions.
Sometimes once you run a command from textbook, for example, in following weeks we're going to have a cost function and a bug function, simply trying to find the shortest way to reach a goal point. So sometimes you will have or you will get some errors or bugs. So if you visit that group page, you'll see you're not the only one. You might see my question or former students' question from the Dr. Cemşit's class as well. So just go through the web page and still you couldn't able to find any solution, just shoot me an email.
Yeah, please put this on the blackboard.
Sure.
So students can access it. So here's some examples. This is a translation of 0.50 and 0, which is here. And notice that rotation metric is identity, which means there is no rotation. And if you have a rotation of 90 degrees above the y-axis, rot y pi over 2, you have this as the rotation matrix with no translation. Such transform may concatenated by multiplication. For example, you have a translation of 0.500 followed by rotation, followed by another rotation around the z-axis of minus 90 degrees. Total is this. So you are really multiplying three matrices here in one line. And here is some more examples. You convert angle and vector orientation to a rotation matrix, or you can, for example, load a map. Later on, when you do the toolbox for mobile robot, I will give you problems like this. I give you a dimension for an environment, and so many in 2 dimensions, let's say, and I put a bunch of arbitrary located obstacles. And you need to write your program, go through the toolbox, and move your robot from point A to point B without hitting those obstacles. Something like that. So you will do a lot of things. So you do a lot of mapping.
If you look at the commands, for example, it's really straightforward and easy. For example, this one.
Create navigation object using the bug2 command. Remember the Volkswagen bug? You have one of those here in the toolbox. Okay. Set the goal, 50 and 35, and then animate path to 2010. So
in the down, you see.
This is here. You go to 20 and 20.
It goes to the 50, 35.
Let's see, you go 20, it's supposed to be here?
No, it goes to, the goal is 50, 35.
Oh, you go, the goal is 50 and 35, which is here. So this is your robot. It's moving obstacle, is avoiding this obstacle and goes to the, okay. You'll see a lot of these things. And later on when we do navigation and localization of mobile robot, which is the toughest problem in mobile robotic part, versus inverse kinematic of a manipulator robot, you have estimation of the location of the robot. In the old days when Columbus came to America, they had no GPS. Okay. What they did, they were just going close to the coast of let's say Europe until they reached Greenland or later on Canada and so forth, and they looked at structures or something on land and used that proximity to adjust it, find out where they are located. Okay, but in today's technology, we will show you how to use Kalman filtering to estimate where you are located. Okay, and this is the command in the toolbox for extended Kalman filtering. Kalman filtering is basically a stochastic optimization problem of an optimal estimator problem. Those of you who take a linear system, you know what observer is, what estimator is. Kalman filtering is the optimal stochastic version of estimator problem. Okay, but Kalman filtering is good for only linear system. But robot is non-linear inside out. So what do? You linearize the model around the trajectory, and then use a version of Kalman filter called extended Kalman filter, okay, which is designated for nonlinear system. We'll go through that later on in the book. Okay. Now let me see. I want to go to chapter 3 of the Fool's book. This book, this chapter is, as you can see, it's difficult to see, but I won't do it that way. Maybe I can even do 120. Anyhow, as we said before, robot, in order to move from A to B, it needs to have some dynamic model. So far, we have not shown any dynamic representation for the motion of the robot. Okay. In your homework number 1, I gave you reference how to write a set of differential equations for a tooling, for a one-link and two-link inverted pendulum. Okay. This chapter gives you a dynamic model for 6-link robot, for an industrial robot. It turns out that it's going to be a 12th order nonlinear differential equation. 2 nonlinear equations per link. And you have 6 links or 6 joints, you get 12 nonlinear differential equations. And they are based on the application of Newton-Euler or Newton-Lagrange equation. Okay. And both of those equations are covered in this chapter. It's not in Cork's book, it's in here. So, let me take you right to the actual situation. And okay, here is, let me see. Let's look at the potential energy of a robot manipulator. The total potential energy of a robot arm, let's say P, let each of its links potential energy be Pi. So typically, Pi is, this energy is a combination of mass times acceleration. And the reason you have potential energy is because of the gravity of these mechanical links. Okay, and they're in the free space. They have energy. They have potential energy. So Pi in this expression is actually going to be a set of n equations shown in this fashion. Ri is the vector from the origin of the base coordinate system to the ith coordinate, ith link. Okay, that vector, Ri, which is equal to the Denoven-Hartenberg matrix times the magnitude of that vector. So this is now the total potential energy of the manipulator is sum of all the subsequent potential energy of each link and or joint Pi, P1, P2 to Pn. Okay. And G is going to be given as a fourth dimension, Gx, Gy, Gz, the three coordinates of the gravitational acceleration G, which is 9.8062 meter per second squared. The zero is because you have a dummy 0 and 1 vector at the end of the transformation matrix. The motion equation of the manipulator, here is what you have. Lagrangian function L for any given robot is equal to kinetic energy minus potential energy. So L is equal to 1/2 of all this kinetic energy, which is a complicated matrices, which is is given. Remember in your physics courses and or your dynamic courses in undergraduate, those of you know, in the undergraduate students, have you all taken dynamic course? Okay. Have you taken it second year or fourth year?
Second.
Okay, that's good. That's good. Because some of the students are just before graduating, they take dynamic. I have no idea who advises the student. Okay. So, you might as well not take it and graduate. Okay. So, what you have, kinetic energy used to be what? Mass times velocity squared. So here is a combination of mass, which is the inertia matrix. This is velocity squared, right here. And this, of course, is mass times distance. Okay, mj times this distance. So this is the Euler-Lagrange equation right here. The torque impacting the motion of a given mechanical system, Ti, is the total derivative of the partial derivative of the Lagrangian with respect to velocity minus partial derivative of the Lagrangian with respect to the position. So your independent variables in this equation are really three. Is time, is position, is velocity. When you have one independent variable, as you know, you're dealing with ordinary differential equation. If you have time and space, time and velocity, time and position, your partial differential equation. And those differential equations are in the nature and represent many phenomena. You are electrical engineers. You know what transmission line is, going from electricity. If you want to model a transmission line, it's a partial differential equation. One independent variable is time or propagation of the signal. The other one is where it is on the line, a space. Okay, there are two variables. This one is more complicated than that. It's a 3 independent variable. Of course, you can argue that it's really this one because Q and Q dot are related together. So you have to go through all the calculation. This is the compact form of the dynamic model of a manipulator. The torque vector is the inertial matrix. Okay, if it's a 6-dimensional, 6-degree of freedom robot, this metric is 6 by 6 times the vector of acceleration, 6 components for Q double dot, plus a nonlinear function h defined in a minute, function of Q and Q dot, plus another nonlinear function of Q. So tau is the torque vector up to n degree of freedom or n joints. Q is the vector of joint variables. If it's revolute, all of these are angles. If it's not, a combination of distance and angle. And this is the velocity, this is the acceleration. And then this is the definition of elements of the inertia acceleration symmetric matrix. H is Coriolis and centrifugal force vector. Coriolis and centrifugal force vector. And in your toolbox there is a command just for that part of the equation. There is also a command for the inertia matrix. And there is also a command for C, which is gravity. Okay? This particular component in this equation doesn't apply, this gravity doesn't apply when the robot is in the space station. Gravity is almost 0. Okay? So that up to here is, you can cover this. This is not relevant for a space application of robot. And if anybody in the class is interested in a space application of robot, come and see me. I'll give you a book, free of charge. Just give it to you. You can read all about it. Okay? It was published by one of my former PhD students at Johns Hopkins. Okay, so this is the elements of D. D11, D16, D22, all the way to D26, and all the way to D66. This is Coriolis. You see how complicated it is? The toolbox that gives you numbers. And this is H. This is H. And then here is gravity. 6 of those. And this shows how much calculation you have, what kind of complexity you have with the computation of Lagrange Euler equation of motion. How much calculation you need to do. Of course, this book was written in the 1960s. Okay. Nowadays, you don't worry so much about computation time. For a Turing robot, we will do that in the next lecture. Okay, let's try to continue our discussion on the let's say tooling example. Here you have a tooling example which is very simple, like this, a tooling robot. You have two joint variables, theta 1 and theta 2. You have two links, L and L here, two links. And you have 1, 2, 3 coordinate system. This is the base coordinate system. This is the joint 1, or you call it the shoulder, and then you have one in the workspace, Cartesian space. So the Denoven-Hartenberg matrix from base to the first joint is given by this. And the same matrix from joint 1 to 2 is given by this. You multiply those two together, you get this equation. Okay. And then, of course, Ci is cosine of theta I, Si is sine of theta I, Cij is cosine of theta I plus theta j, and so forth and so on. And then the Q matrix, which is a convenient way of compacting the equation, which is so complicated, is given by this part of the presentation. So U11, which is a measure of the velocity, partial of angular velocity, partial of the DH matrix by respect to theta 1, U21, partial of second A0 and 2 with respect to theta 1, and theta U22, partial of A20 with respect to theta 2, and finally, okay, then of course it's symmetrical. Therefore, you come up with this equation. You form the inertia matrices, J1 and J2. Inertia, this is inertia of link 1, inertia of link 2. And they should be similar to what you see in that book, that file I sent you for double pendulum in homework number 1. Very similar to that. In fact, if you go to that section, you see the derivation of dynamic model of a double pendulum using Lagrange-Euler equation. This that. Okay? Finished? Is equal to this times theta 1 double dot and so forth, plus Coriolis plus gravity. And what you see here, you have theta 1, theta 2, theta 1 dot, theta 2 dot, 4 state variables. 4 state variables. You have a fourth order nonlinear ordinary differential equation. This is in the command tooling in the toolbox. It has actually implemented this dynamic model to find the trajectory of a tooling roller. Okay. And of course, in your experiment number 1, you will repeat homework number 1 in the lab. And you will do one link and 2 link inverted pendulum. So this is essentially dynamic model of your 2 link inverted pendulum type. Okay. It's not exactly this because this is hanging down, inverted pendulum going up. Okay. But nevertheless, you're supposed to do a linearization around that point, 180 degrees up, and then solve your control problem. Do your. Okay. We'll see you next time.